To understand what limiting reactant problems are all about, it's a good idea to take something that you can visualize easily and first of all think about that. So we're going to think about what it takes to make a bicycle. To make a bicycle, you need one frame, two wheels, two pedals, a seat, and one set of handlebars. Now suppose you are supplied with 62 frames, 128 wheels, 250 pedals, 50 seats and 58 handlebars. What's the maximum number of full bikes you can make? Now, I'm sure that most of you can look at this and come up with the answer in your head, but let's just work it through a little bit. One frame plus two wheels plus two pedals plus one seat plus one set of handlebars gives one bike. Now, if we've got 62 frames, that would allow us to make 62 bikes. 128 wheels would make us 64 bikes because we need two per bike. 250 pedals would give us 125 bikes. 50 seats would give us only 50 bikes. 58 handlebars, 58 bikes. Now, looking at that list, it's plain that we can in fact only make 50 bikes with lots of parts left over. The 50 bikes is the maximum we can get. That means that the 50 seats, which is determining the 54 bikes here, the 50 seats are what we call the limiting number, the limiting component, or in the case of chemistry, the limiting reactant. Well, now we're going to look at an actual chemistry problem, and this problem is a very typical one. It tells us that we are reacting ammonia with oxygen to form nitric oxide, NO, and water. Notice that the equation is balanced. This is essential. You can do nothing without the balanced equation. We are told that for this reaction we are given 1.5 grams of ammonia and 2.75 grams of oxygen. There is a big clue straight away that this is a limiting reactant problem because we are given two quantities, one for each reactant. So one of them in all probability is going to be too much. We want to find the limiting reactant, the one that is going to be all used up. The limiting reactant determines how much of each product we get. So this question first of all says, which of the reactants is limiting? And then how many grams of NO are formed, how many grams of water are formed, and then we want to know which is the excess reactant and how much of it is left over. We have a reaction of ammonia with oxygen gas producing NO, nitric oxide, and H2O, water. The question tells us that we are supplied with 1.50 grams of ammonia and 2.75 grams of oxygen. Okay, so what do we do here? The first thing we must do is convert these masses to moles. That's because our balanced equation deals only with moles. It does not deal with masses. So our first task is to take 1.5 grams of ammonia and convert it to moles. 1 mole of ammonia has a mass of 1 nitrogen, 3 hydrogens, 17.03 grams, and that gives us 0.0881 moles of ammonia. Okay, we do the same for the oxygen. we have 2.75 grams of oxygen, and converting that to moles, we simply divide by the molar mass, which of course is 32.0 grams. The grams go, and we have 0.0859 moles of oxygen. And notice that I have paid attention to sig figs. 3 sig figs for the masses that were given, 3 sig figs for the moles. Now, we're only just started, because we have to now use those quantities to figure out how much product we're going to get. Now, to choose the product, you have to decide on one of the products. In this case, we've got NO and we've got H2O. It does not matter which of those you focus on. You just try to choose one that is the easiest. I'm going to choose the NO because it, as you will see, makes some of the calculating a bit easier. So the first thing we do is we say, okay, let's start with the ammonia. I'll just write ammonia here so that you can keep track of what we're looking at, ammonia. And we are going to say we have 0.0881 moles of ammonia, and we can see that that means that we will have the exact same number of moles of NO, because the ratio in the equation is 4:4. So that's going to give us the same moles of NO. Now we do the same thing with the oxygen. So here is the oxygen. We have 0.0859 moles of the oxygen. This is going to give us, for the NO, now this time the ratio is 4:5, so we have to do a bit of calculation. 0.0859 moles of oxygen, and that's 4 NOs for every 5 oxygens. So the oxygens go, and this gives us, when we multiply it out, 0.0688 moles of NO. Okay, so this is now where we need to look very carefully at what we've got. You will see that this is 0.0881 and this is 0.0688. This is the least amount of product, and that means it was produced by the limiting reactant. So therefore, the limiting reactant in this case is the 2.75 grams of the oxygen. So that is the answer to part A. The limiting reactant is the oxygen of the NO. Well, we've already found that the moles of NO are 0.688. That's moles of NO. So we can easily convert that to mass using the molar mass. And NO is quite simply 1 nitrogen and 1 oxygen, so the mass is 30.0 grams. And so this comes out to be 2.06 grams of NO. And that's all there is to that. Now we want the mass of the H2O. Well, a little bit more work here, because now we have to find the moles of H2O and then the mass. So we go back to the fact that our 0.0859 moles of O2 was the limiting reactant. The limiting reactant defines everything. We look at our balanced equation and we see that we have 6 moles of H2O for every 5 moles of O2. Those moles of O2 go out, giving us 0.103 moles of H2O, and we convert that to a mass, 0.103 moles of H2O multiplied by the molar mass of H2O, which is 18.0 to 3 sig figs, and this gives us a total of 1.86 grams of H2O. Of course, these two lines could all have been done in one if you wanted to. So now we're on the part where we want to know how much of the excess reactant is left over. Now, if O2 is the limiting reactant, it must be that the ammonia is the excess. The excess reactant, I'll just label that ER. Now, there are various ways you can do this. You can do stoichiometry again if you want to, but a quicker way here is to use the conservation of mass. And what this means is we say that the mass of the products equals the mass of the reactants in the reaction. That is to say that the mass of the NH3 plus the mass of the O2 is what gave us the mass of the NO plus the mass of the H2O. So that therefore the mass of the NH3, and this is reacted, don't forget, reacted, this is not left over, 2.06 plus 1.86, all these numbers are above, subtract the 2.75 for the oxygen that was given, and this comes to 1.17 grams of ammonia. Okay, so that is what was reacted. So therefore, the ammonia remaining, NH3 remaining or unreacted, is equal to what was supplied, which you will recall is 1.50, subtract 1.17, and this comes to 0.33 grams. So that is the mass of the excess that is remaining. Well, that's the end of this video. Thank you for listening.